and clearly they are disjoint because here it's a set of the points Z belongs to X such that f z less than R, and that one it's a set of the points Z belongs to X such that f z greater than R. So there is nothing common between A and B. So they are disjoint. So now we show that they are open sets. They are open sets. So one can easily see that now this A, what's this A actually? It's equal to F inverse. It's the inverse image of it's less than R, so it's minus infinity to R. It's inverse image of this set, and B is equal to inverse image of it's greater than R, so R to infinity. You can easily verify this. A is the inverse image of this interval, unbounded interval minus infinity to R, and B is the inverse image of that interval R to infinity, unbounded interval. And you know this this is an open set in R. This one it's also an open set in R, and F is continuous, inverse image of open sets open, therefore A and B are open. Thus A and B are open sets, as F is continuous, so therefore inverse image of open sets open, and these two are open, minus infinity to R and R to infinity are open in R, They are open sets in X here. They are open sets in X. Also A intersection B is the phi set. So that means for any 2 points X and Y in X such that X not equal to Y, for any 2 points X and Y in X such that X not equal to Y, there exist open sets, disjoint open sets A and B such that X belongs to A and Y belongs to B. So therefore X is Housdorff space. So thus X and Y are separated by disjoint open sets, and hence X is Housdorff. Space. X is Housdorff space. Okay. So this X is Housdorff space. So next we define again the new class of topological spaces. So let's define a completely regular space. Completely regular space So what do we mean by completely regular space? A completely regular space or it's T3.5 space, or it's also called a Tishnov space. A completely regular space, or it's a T3.5 space. So it's first a T1 space, First it's a T1 space, and it has one more property, with the property that if X is any point of X, if X is any point in X, and F is a closed subset of X, and F is a closed subset of X such that X is not in F. So a completely regular space which we also call T3.5 space. It's first a T1 space with the additional property that if X is any point of X and F is any closed subset of X such that X is not the point of F, then there should exist a continuous map. Then there exists a continuous map F from X to the interval 0, 1 such that it maps X onto 0 such that f of X is equal to 0 and maps each point of F onto 1. Image of whole F is equal to 1. So that's the definition of completely regular space. So this X is completely regular space if for any point X and if any closed subset of X where X is not the point of F, there should exist a continuous map from this set to interval 0, 1. There should exist a continuous map F from that topological space X to the interval 0, 1 such that it maps X onto 0 and this closed subset onto 1. That's the definition of completely regular space. So in the next it's an exercise. Every completely regular space show that every completely regular space is Housdorff space. It's very simple. So let's prove this exercise. Solve this exercise. Every completely regular space is Housdorff space. So here is the solution of this exercise. Let X be completely regular space. Let X be completely regular space. Now we show that X is Housdorff space. So for this, let's choose any 2 points in X. Let X, Y belongs to X such that X is not equal to Y. Then this singleton Y, since X is completely regular, therefore it's first a T1 space, and in T1 space every singleton set is closed. So that means this singleton set is closed subset. Of X as X is T1 space. Now we have two things here. One is the point X and second is the closed set Y such that X is not in Y. So now we have this X is not in Y and Y is a closed subset of, and Y is a closed subset of X. Therefore, by definition of completely regular, by definition, let me write here it. So by definition of completely regular space, which is X, so there exists a continuous function, f from X to the interval 0, 1, which is a subset of R, so it's also a function from X to R, such that f of X, it maps X onto 0 and it maps the closed set y onto 1. So that means f of x is equal to 0 since it continues on the one point y. So that means this f of y is equal to 1. So which implies f of x is not equal to f of y. So for any two distinct points x and y, we have a continuous function f from x to r such that f of x is not equal to f of y. So thus c of xr separates the points x and y. So therefore any two points of x are separated by some continuous map, and hence by this theorem, which we have already proved, that if any two points of a topological space here, if x is a topological space and any two distinct points of x are separated by CXR, then x is Housdorff. So therefore x is Housdorff. Therefore x is Housdorff space. So this proves the theorem. Thank you.